Hey guys, I hope everybody's doing okay. So I've got another little video for you here. Well, perhaps not so little on this one, if I'm really honest. We're looking at three-phase rectifiers that I've been testing different ones for my Gasser helicopter, which is a petrol helicopter, RC helicopter charging system. I gotta be honest, I've done some testing already. I've saved the best one till last because there could be smoke. Probably not really designed to do this. The circuit itself is designed to maintain a constant 63 to 80% charge of the flight battery. However, I've drained the battery right down, and we're going to see if it can actually charge and supply the 1.5 amp current that the helicopter needs to run without blowing anything up, I guess. So, without further ado, let's see what we've got on the bench. So I think it's fair to say we've got quite a busy bench here and quite a bit to walk through. So first of all, let's have a look at what we have. So we're trying to replicate on the bench the RC helicopter, which is here. Gasser engine, two-stroke petrol engine here. And essentially what we're trying to replicate is this bit up here. So this motor sits on top of that engine, if you like, spins at about 12,000 RPM in normal flight, and the purpose of this is to maintain the state of charge of this battery. 80% is ideal, and under my normal flying conditions it should do that. This circuit on the bench should do that. If you're pushing it hard, it might drop down to about 60, 63. But just to give you a little bit of indication, we're going to look at some statistics in a moment, but an 80% charge would actually last this helicopter at least 50 minutes of flight time. So even if this fails, you've got plenty of time to land, and the telemetry in the system that I've built will signal to the radio and cause the radio to vibrate should there be any sort of charging issues. So lots of time. So if it did, what I'm trying to get at there is if it did go down to 63% or 60%, then you're still going to have lots of time to land and plenty of warning issued on the actual radio transmitter itself to tell you that there was a problem with the charging system. So what have we got on the bench? So we've got on the bench, we've got a motor in here, in here, which is taking the place of the engine. It's going to spin up at 12,000 RPM. We've got it here on an ESC around the back here, and it's being powered by a 5,000 mAh 6S battery. On the top of that, we've got, just like we've got on the helicopter itself, we've got a dog with a magnet in it and a Hall effect sensor to detect when the magnet passes. That Hall effect sensor feeds back to an ESP32, so we know what RPM. Got a little bit of a governor. I'm not using a PID loop, I'm just using a factor loop, so it calculates the error against what we're trying to get to, 12,000 RPM, and just keeps adding a factor to the pulse width modulation to drive that and try and keep it approximately 12,000 RPM. It doesn't have to be precise, because when you're flying the Gasser, you don't get a constant head speed. You do get, as you alter the collective management, you can have drops of at least 1,000 RPM, if not more, or an increase indeed of 1,000 RPM. So a little bit of variance on that doesn't really matter. On the top of this test circuit, we've got exactly the same motor as we've got on the helicopter, which is a Turnigy D2830 stroke 11, 1000 kilovolt. So kilovolt at 12,000 RPM, you'd expect it to make 12 volts, but of course it's not 100% efficient, far from it. So you're probably going to get more like 10, or we know we get more like 10 with the testing. This motor is attached to the rectifier. Now this is what we're testing. So on my first beta testing of this helicopter, I was using some diodes. I was using some 10SQ045 diodes, and what I wanted to try and test is what happens if I change that three-phase rectifier for different types. So these are 1N5400 rectifier diodes. We've got some S5H100 surface mount diodes, rectification diodes, and somewhere I have got, and where have we lost it? I've lost it now. We've got some more. Where's the other one gone? One moment, please. Ah, here we go. It's here. And then we've got the dedicated package, like this. So this is probably what you'd normally do by a package. And this is an, I don't know if you can see that, but I'll read it out for you just in case. It's an SGBJ 2516 three-phase rectification circuit. And my testing has been done on all these, and frankly I don't like this, to be honest. And this one here is going to be the best. It's made up exactly like this. They're just bigger diodes. They are 20 SG045. Let's have a quick look at the statistics of why I've chosen that before we go further down the circuit. So these are my test notes, and this is the circuit we've got. This is the motor that we've just been looking at. This is the three-phase rectification circuit. So these are the 20 SQ045 diodes arranged in this order, so I can take the AC signal coming in from the three wires from the brushless DC motor into this and create a rectified output. There is a capacitor built in to the into the BEC here, and I'm leaving it that, although there is a sort of a half volt peak to peak difference here, so I may decide to add a little bit more capacitance on there to smooth that out a little bit. Not sure yet. I've got this 10 SQ045 diode here. This is just to protect any back current coming here because we've got the battery. This would be the load of the helicopter, and on this pin here, I've joined the 7-volt pins, which you would normally just bridge with a jumper. I put a 3K resistor on that to get exactly 7 volts, and that's so I can precisely tune the voltage that I want across here, and of course the load across on my helicopter, because I want to aim for about 6.7 volts. The different types of rectifiers I've used here are all monitored here. It's all detailed here, sorry. And these are the different types, and we're looking at the temperatures and the voltages that are presented at this stage here after the rectifier, and if there's any peak to peak differences. What you do see is that when you do the anticipated worst case, and of course I've been flying now for some beta testing, so I know what voltage I'm doing now. So when I first did this, I was aiming for sort of 3.5 amps to 7.5 amps current, where I now know that really a 1.5 amp to 2 maximum really is the standard sort of flying type current that we need to generate and keep the battery maintained. So I've done sort of worst case scenario here at 3.1 amps, and you see the temperature of the rectification diode or circuit, depending on which one we're using here, is significantly different, I guess, here, because these are in the 40s and this only got to 26. I did repeat this test several times just to prove that it was definitely correct. And I'm just using cheap AliExpress diodes here, guys. I've not really got them from a particular fantastic manufacturer, and as I built this circuit, I probably will get some better ones from a decent source just to make sure they are top quality. But it's absolutely for sure that I'm better off sticking with my sort of original sort of design and going with these rather than going for anything better. Even though I do like these surface mount, I just think they look a bit more professional. But at the end of the day, temperature is what is required to be as low as possible, because remember that this sits inside the canopy. And if I look at some of the before we move on to that, actually, if we just look down here, we got this. This is the RPM here, and this is the worst case scenario with the S5H100 rectifiers, which is basically these little surface mount jobbies, and we see here that the rectifier goes up here, what we're talking there, we are talking into its 40s here on this particular circuit. It was 43, I think. And then this is the ones I've chosen, and you can see the difference in temperatures here. In fact, the grey line, which is the protection diode, which is this diode, is actually getting hotter than the rectifier itself. So this is an awesome result, considering that inside the canopy where this circuit will sit, there's a plus 25 degrees C to the ambient temperature. So you could really be looking at a sort of 45 degree. And if we go up here, we've got some other graphs here for canopy temperature. So we've got canopy temperature, the BEC temperature, engine temperature. This is flying with and without canopy. So here you've got the without, and then you land, put the canopy on, and take off again, and it quite quickly zooms up because of the heat of the engine. So this is interesting. And also just run by this, because this is quite interesting too. So this is the RPM. This is the clutch RPM, and the pink line is not really plotted very well actually in this graph. But if we just look at the clutch, that's when the clutch bites. And we see if we do a pitch pump, which is where we alter the collective really high to really push the RC helicopter to climb heavy, we can see that we get a clutch slip. So that's really useful. But most importantly here is we see different results here. So we've got blue line, the receiver voltage. We've got the pink line, the BEC voltage. We've got the green line is the cells monitor on the battery. And the RXBT voltage is the red line. And what we can see here is that when the receiving voltage and the BEC voltage falls off due to a motor slip here, then we can see down here the battery just starts delivering the current instead required, and then it swaps back over to the generator and should then top back up the battery at the same time to keep the battery nice and topped up for the next time it's required. So this is what I'm trying to build, and it has been successfully working. Although it's in beta with a lot of sort of discrete components being used, not much surface mount stuff, and it really needs a proper circuit board to carry on. Really, let's go back to the bench and discuss the circuit more. So we've got this coming down here. So this is the rectifier of choice. And then we've got, it runs into the BEC, as we saw on that circuit here. Take it around here. These are the temperature probes, by the way, guys. Just using simple LM35s. We don't need to be so accurate here because, frankly, if we're into 1 or 2 degrees, then we've got a problem. So that they all feed back into the ESP32 for monitoring purposes. Let's clear these out the way. Don't need them anymore. We come round here. Other side of the BEC comes out. We go through this what's up meter. Just here, I've just got a bulb as a standard load. This will take about 1.3 amps. This bulb on its own. And during the testing, all I was doing really is adding more bulbs to pull more current. At the same time, we go along here, and we go into the battery. So that's along here, and then these 2 meters are measuring the voltage across the battery and any current going either in or out of the battery. So here what we've got, if it's going into the battery, then it will be a minus figure, and if it's going out of the battery, it will be positive. Okay, so there could be smoke here, guys, because this battery is at its lowest state of charge. That, well, technically with this circuit it shouldn't be this low, because it should always be between 60 and 80%, generally 80% with my flying. But I think that if we just reset it so and get the, here we go, if we just get this monitor plugged in here and we plug it in, and it's a Li-Fi battery, so I'll just change it from LiPo to Li-Fi. It's at 25%. So that's really quite low for this Li-Fi battery. Okay, so we're gonna try and start this up now. I'm expecting there to be quite a current demand here as it tries to bring this voltage back up. as well as trying to keep this bulb alight, which is basically the power the helicopter needs to run. What we want to see is that we don't go below 6 volt. We've got that on the oscilloscope too, so as I can see it, and that's rolling across the screen. So I should be able to see that if anything drops ultimately low. Of course, if you think that if it was to drop, then anything could happen to the helicopter. It could completely lose control of the servos, which keep the blades in the right order. It could topple over if it was spinning up and the voltage fell below about 6 volts. I wouldn't want it below 5 volts. Certainly would be critical. So without further ado, I'll set this all back up, and you can join me again as I start up the test. Okay, so this is quite tense. So I'm going to connect up the battery like this. So that's the main power supply to the simulated engine. You can make sure this is ready to connect up. It is. So I'm going to start up the program to trigger the motor to start up and start spinning. And then once it starts to spin, I will connect up the bulb, if you like, to simulate the power required for the helicopter. And at the same time, I'm going to be trying to keep an eye on these meters down here in the bottom corner, and in particular this one here, to see how much the initial amp draw is as the helicopter starts up, if you like, to see what it tries to do with this battery. I am aware I'm sat quite close to this here battery, so I might just stand up rather than so I can evacuate quickly should something go wrong. So let's just pull that out of the way. Let's have a little bit of run space. I do have a CO2 fire extinguisher at the ready just in case, although it's quite a small space, so need to be quite careful and not breathe if I need to activate that. Okay, so without any further ado, let's see what happens. Okay, the circuit has been told to start up. The ESC is activating as we speak. Okay, the bulb is lit. I've got a minus here. It's all seems to be doing quite well actually. I've got if you can hear this, I've got 1.58 amps down here. I'm sorry it's quite noisy. If you can't hear this, I'll tone it down and put the numbers on the screen. Everything seems okay. I'm just going to look at what the graphs say. So we're running at 12,000 RPM on the screen. Can I just jump that to desktop only? Hopefully you can see that. So that's what I can see on the screen. You can see the RPM here and the temperatures building here as this goes up. Back to the main screen. So okay, so still on a minus 24, so that's got to be going into the battery. %60 charge is showing on the battery now. 6.65, 6.61. So this is good. I'll speed this up a bit, guys, just so you are not watching all the rubbish we've got here. %65 charged. Protection diode still high. We've got this going nice. It's running very well actually. It's all running very cool. It's all really very cool. This program is available from my GitHub page. We can see here that we've got the switch mode power supply, usual thing here, going off, which is gonna difficult to get rid of this, to be fair. So that's what that is. Just the switch mode power supply. So we've now been running for almost 10 minutes. And we can see that the the temperatures have leveled out here. Nothing to worry about here. So we're happy with that. Now on 68%. We're now drawing about 3.1 amps. See this as we turn this here. We dropped here back down to 50%. 50%. Struggling to put anything in the battery by the look of it. 3.2 amps here. That was hot. So I think what we're getting to see there is if we were using at pretty hard, full, worst case scenario, drawing 3.1 amps of power needed to run the helicopter, we found that we weren't actually charging at all. If we do that again, you see the charge, you can't keep up with the charging. Let's go back to the desktop. And we see this little diode here, this one here, is this diode here. Okay. What's our battery looking like? 67% here. 67%. Drawing about 2.15 amps now. Seems to be stabilizing out here. A little bit these around here. Okay, that's warm. The motor itself is warm. Feeding in about 0.1, 0.2 maybe of an amp maybe. See what this battery's reading now. Got 69%. So I think all in all, that's a successful test. I mean, this is heavy load. Let's put it back to normal load. So if I unplug this, plug this back in. It's now it's at half an amp going in. Okay, so I'm going to try and draw this to a close. We're still charging at 1.8. It's looking good. 6.64. I never saw it drop below the minimum. So let's stop this test. So we've took the motor off. We can see that we ended up at about 21, 24, 27 on the protection diode. So I think what we learned from that, let's just see what this motor is. That motor is fine. It's warm. It's not hot by any means. Warm at the most. That's our battery ended up at after that test. Let's have a quick look at how long that ran for. That ran for, let's say, about 18 minutes. That test ran for. Now the live feed is showing a very... Oh, that's because I've still got this connected. That was a bad thing to do because that means I've lost some data there. I left the bulb connected, which was just drawing straight out of the battery. So it's dropped it back down to 17%, which is a bit of a shame really that I left that in there, because it does drag it down very quickly. Let's see what it recovers to though. I think ultimately I'm very pleased because nothing left gave us any magic smoke. I was pleased with all the oscilloscope data, because all I could see there was this switch mode power supply, which is basically what this BEC is doing its thing. You always get that anyway. Very difficult to smooth that out. The hottest thing was the protection diode here. That seemed to go up to about 30 degrees, but to be fair, that was fine. These are just barely warm to the touch. To be fair, everything seems to have gone smashingly well. To be fair, there, I'm quite pleased with that. So that can be put back on the heli. So it's come back up to 30%. It's a shame I left that bulb connected at the very end there, because that will have dragged it down significantly. That percentage, so it would have lost probably everything that I managed to capture in that 20-minute flight. But I think what I can be assured of is that over time it would build itself back up to 80%. I think what I'll do now, because I know what voltages this circuit's producing, I can get rid of this bit and just feed straight into here with the bench power supply. If I put in about 9.5 volts, that's essentially what I'm getting out of here as an average, and I'll be able to then leave it going without making all the noise, and see how long it does take for this to actually go up. But back up recharge. I mean, it was only charging at 200 milliamps, so it's going to take quite a while. I was quite pleased, to be fair, that it didn't just suck in sort of 70 amps sort of thing, or attempt to suck in 70 amps. It just seemed to trickle charge it, which I'm quite pleased about, to be fair, because that'll help with the lifetime of the battery, and just charge it up over time. The fact that the circuit was quite capable of feeding everything it required to run the helicopter and just top up the battery was quite good. I'm quite pleased with that. Now, if I wanted to increase that to more than 200 millivolts, to 200 milliamps going in to charge the battery, then what we would do is we would change this. Let me get my Mobius back from the thing so I can give you some close-ups. So on this, this is the you might have seen this on my last video, but if just in case you didn't, this here is a YEP 20 amp S-Spec here, and what we see here is as standard. What we get is let me see if I can swap to Mobius only on this thing. I've got one somewhere, Mobius only. There you go. So what I do is, generally speaking, these pins here at this far edge here. So you've got, join these pins for 5 volt, 5.5, 6, 7, and 9. But instead of using the jumper, placing a resistor across different pins, different values of resistors, you can actually get to be a precise voltage. Because when I select 7, it's actually about 7.2, and I wanted actually 7 here. Through the diode here, the protection diode, then we get to about 6.67 coming out of there. So that's a perfect match for me. But if I wanted to increase the current going into the battery for charging, I would just have to increase that voltage by just a little bit, maybe 0.1, 0.2 of a volt, and that would help put a little bit more charge in the battery, so it would go faster. But just be aware then that when I do that, then it might go over 80% as standard. It might go to 85 or 90, and this is a Li-Fi battery, a PO4 Li-Fi battery, and it's best. It's at its most longevity if I don't take it over 80%, and 80% is about right, because I don't know if I said, but you get about 50 minutes of flight time. So even if everything failed, I would get about 50. If this was at 80% state of charge, I would get about 50 minutes flight time. So plenty of flight time, really. I mean, I could reduce that if I wanted to. And to reduce that, I'd probably just reduce this. And of course, I've got to remember not to have this too high a voltage from here, from this after this protection diode, because essentially what happens here is this bulb is representing all those electronics, and most importantly, these servos here, which are 6 volt servos. So I run them on about 6.7 and they are fine, but I wouldn't want to drive them much harder than that, if I'm really honest. So I hope that was useful. I mean, it was certainly very useful for me. We didn't release any magic smoke. We know that if we do have a bit of a dumb moment and we start the helicopter up with a flat battery, essentially we're not going to do major damage. I was really pleased of how that 3-phase rectifier stayed very cool, even though it was being challenged to get that battery back up to its 80% state to charge. It did only put 200 milliamp per hour in, which is probably on the low side, but I daren't really increase the voltage on that, because, like I just said, the voltage of the servos, it would put a little bit more voltage across the servos, so don't really want to do that. I mean, I think the rule of thumb is, when I first start off with 80%, and it will maintain 80%, and I know that because I've done the tests already. So I think it's not designed charge a flat battery. I think, in conclusion, what I see here is it would eventually charge the battery, but it might take several hours of flying before it got it right back up to 80%. But ultimately, it can do it. It's not going to cause any issues if you did fly with a flat battery. Of course, you've got to accept that if you've got a flat battery and something went wrong with the charging system, then the helicopter may not survive. But that's one of those dumb moments, and best to check the state of charge of the battery before you take off as part of your pre-flight checks. So like I said, I hope that was useful. If it was, please like and subscribe. Thanks for joining me. It's great to see you guys viewing the videos. It really gives me a lot of pleasure. So you guys take care and enjoy your day. Bye bye.